Okay, I want to start off by showing you guys some questions from the diploma that people were asked in previous years. They ask this question almost every year. Okay, so I'm fairly confident in telling you you're going to get a question that looks something similar to this. They're going to ask you, what is the oxidation number for something? And they're almost always going to make it numeric response, because it's a great numeric response question. And maybe I'll just start by answering the diploma question and show you how this works. Okay. If I were solving this one right here, and I want to find the oxidation number for nitrogen, I would consider how charges work. Okay. Hydrogen, what's the typical charge for hydrogen? Usually it's +1. It's usually the charge for hydrogen. Well, if you have 3 +1s on hydrogen, then what would the charge of nitrogen be? -3. Because you have 3 positive hydrogens. So then you're
Randy Bonnet, please call 100. Randy Bonnet, please call 100.
Does that make sense? Well, we'll get to that. So in this case, it looks like nitrogen is a -3. Yes. Let's do the next one here. Skip nitrogen. What's typically the charge on oxygen? Alright, so if oxygen's -2, it means that nitrogen's probably +2. Which maybe is weird, because nitrogen normally isn't +2, but if you look at the chart up there, especially my really detailed chart, you'll notice that +2 is actually a valid charge for nitrogen, even though it's maybe not one we've done in the past. Does that make sense? Again, what's oxygen's charge? Well, normally it's -2, but in this case, then if nitrogen has to be +2, but there's 2 of them, each nitrogen must be a +1. Yeah.
Oh my gosh.
-2 times 2 would give you a 4, so this guy better be a +4. So the answer for this would have been 3, 2, 1, 4.
Okay, I actually don't get it. Oh my gosh, I don't understand why it's -3 for the first one. What?
Okay, so hydrogen normally has a charge of probably +1.
Yeah.
So then in order to balance and make it equivalent in making a molecule, if you have 3 positive charges, the nitrogen better be a -3 to balance it.
Oh, you're trying
To make it neutral?
Okay, you're making it neutral. That makes more sense. Why are you... What?
Okay. Same type of question, different diploma. But you can see, the way they phrased it was almost the exact same. The oxidation number for the metal was what? So, what's oxygen's charge? -2. So that means each sodium is probably going to be a +1. Sodium's by itself now. I actually did this with you guys in the past. What if it's just a neutral atom?
0.
Good.
Oh, good job.
Iron by itself.
0.
There you go. And then if oxygen is -2, that gives you a grand total of -6. Good. Ta-da!
So oxidation
No, they could be -2. In this one right here, we had a -3. They could be positive or negative, I guess.
I don't get why it's 0 though, because it says, but isn't
For the
Na
metal.
itself just +1?
Well, no, Na as an ion is +1, but we're talking about Na in an elemental form. Let me show you a different question here. And I've actually shown you this skill before. I did it to start the unit. I just didn't call them oxidation numbers. I was more or less working with charges. For example, what's the charge of oxygen if it's an atom? I would say it should be 0. Right? But then what normally happens to oxygen's charge? What's its typical charge in the table? -2 is actually the only charge listed. So let's say this oxygen right here was a -2. What would this zinc right here have to have for charge? +2, hopefully. Because it has to balance, right? A -2 and a +2 would
It's just there's
cancel.
2 of those. It's not zinc 2 oxide. There's a difference.
Yeah, we just need to balance just the zinc oxide. The 2 is just about balancing later. Here, if oxygen is a -2, but you have 2 of them, that's a total of -4, right? So that means the sulfur is probably a +4. It helps especially when you have the big table nearby, because you can kind of check and say, oh, I didn't know sulfur could be +4, because your
Noni
data table
Orr,
doesn't
can you
list
please
that.
contact the office ASAP? Noni, please contact the office.
Sometimes you just have to use common sense here. Probably the most likely scenario here is +2 and -2. Right? Because zinc is usually a +2 charge, and sulfur is normally a -2 charge. Well, what I did with you guys when I started the unit is I tried to figure out, well, whose numbers are changing. Here you have 0, and 0 goes to say -2. Is that gaining electrons or losing electrons?
Gaining.
So that means oxygen must be gaining electrons, which means he must be reducing. What other numbers changed? Sulfur. Sulfur goes from -2 to +4. That's losing electrons. Losing electrons means that you're being oxidized. So reading through, did zinc atoms gain electrons? Did zinc do anything? What do we call them?
Spectator.
Good. Zinc atoms lose electrons. No, same thing as before. Sulfur gains electrons. Nope, sulfur loses electrons. Does that make sense? I've actually kind of shown you this before. I just never called it oxidation numbers. So let me just walk you through some basic notes on them. Oxidation numbers are considered to be a way of electronic bookkeeping. Okay? It's very, very similar to like charges. Sometimes you might see the word apparent charge. How do I want to describe this here? I guess I'll just read this here. Apparent charge is what we use to, like how we call it, because sometimes it is literally the same as the charge on the atom. But the reason why we call it like an apparent charge is that molecular compounds are different than ionic compounds. Remember how ionic is like a cation and an anion? You have a positive and a negative. Molecular compounds really don't work that way. So for example, when I asked you to do, say, NO, that wasn't ionic, but we're like pretending it was ionic. Does that make sense? And trying to figure out what the charges on each of them would be, but it isn't actually ionic. Does that make sense? So, long story short, it's not charges, but it kind of is, isn't it? So like we're just pretending that they have charges. So that's just the name we call oxidation numbers. They're not the actual electronic charges, but they're often the same. Okay. For example, if you have an ionic charge, if you have Fe2+, its charge would be 2+. Here's a chart that I pulled out of, I think, your textbook that just kind of goes through just some basics on how you'd find charges. Let's say it's an element. Often when I'm starting with you guys in like grade 11 or grade 10, I always reinforce the term atom versus ion. You guys remember me talking with you about this like a lot a year and a half ago? Atoms are neutral, ions have charges. If I give you Na in its elemental form, that is an atom, it has no charge. If I give you chlorine as part of Cl2, those are atoms, they have no charge. But if I were to give you, like, say, this molecule here, HCl, H is +1, Cl would be -1. Why? Well, now because it's forming its ion rather than by itself. So if you're by yourself, you're a 0. Hydrogen is typically a +1. I have never seen this before, but it is theoretically possible for hydrogen to be -1 if it's bonded to someone less electronegative than it. Here's the only example I know of, lithium hydride. In this case, lithium would be +1 and hydrogen would be -1. It's rare. Never seen it on a diploma, but it could come up, who knows.
How do you know which one to start with? Because like, where's like the number one?
So
So would you use like, because I'm just confused, like, because if you think the hydrogen has a +1, then you would put the lithium as a -1.
that doesn't really seem to fit as well though, because does lithium really ever have a -1 charge probably? Like lithium doesn't really want to gain more electrons, it wants to lose the one it has. That makes sense? Like remember lithium, like when we draw these dot diagrams, lithium has 1 electron. It would really like to lose that 1 electron probably, rather than gain it. Maybe the better way of doing it is, remember bonds from last year? We would look up electronegativity numbers. So hydrogen I think is 2.2. And then lithium, can someone find me lithium's electronegativity number? It's not on that table, so. It's probably like 1.2 or 1.0. One thing we talked about last year in the bonding unit is the electronegativity number determines who steals the electrons. So who wins in this fight here between hydrogen and lithium? Hydrogen does. So that means hydrogen has these electrons are really more towards hydrogen than lithium. So then hydrogen becomes negative and lithium becomes positive. We use the notation like this little symbol here, slightly positive, slightly, this one should be negative. Remember that from last year at all?
Not the slightly thing.
There was a symbol we used here, like whenever you did a bond, like say H with Cl, we draw like an arrow towards chlorine, saying chlorine is the negative side, hydrogen is the positive side. Okay. We're probably making too much out of this
Okay.
because it's pretty rare. The only time this will matter is if hydrogen gets bonded with like one of the metals in group 1. So like if it's hydrogen and lithium, hydrogen and sodium, hydrogen and potassium, then hydrogen might be negative, but it's pretty rare. Oxygen is pretty much always considered to be a -2, but just like with hydrogen, there is actually one exception. It is in hydrogen peroxide, which is H2O2. The way it works here is that oxygen gets to be called a -1, and hydrogen gets to be called a +1. That's kind of the only way it'll balance out, right? Hydrogen would be +1, oxygen would be -1. So otherwise, we pretty much always go with oxygen as -2. And if it is an actual ion itself, it's the charge on the ion. That makes sense? Just do a lot of examples.
I don't get why the peroxide H2O2 they both have to be 1 then.
Well, because, I mean, if you have 2 +1s, you're going to need 2 -1s to make it
It
balanced.
doesn't make sense that.
Well, I mean, if we tried to make oxygen be -2, then you need to have hydrogen be +2, and hydrogen typically wouldn't be a +2 then. So we've defined this oxygen here to be a -1.
Okay.
It's the more likely possibility there. Again, that's an exception. Almost always oxygen wants to lose 2 electrons or gain 2 electrons. Maybe here's the thing that was catching, I think, Hannah, you at first there. The idea here is that the charge for a compound needs to be 0. So like if it's NaCl, this is minus, this is plus. If it's NH3, if this is +1 3 times, then this has to be -3, so the grand total of the thing becomes like neutral and 0 and balanced.
If there's like a prefix number,
Like a
that
coefficient,
doesn't
not
count.
relevant. That's only for balancing. Okay, let's just hop ahead to some examples here. Let's try to figure out some of these numbers. So, HCl. Well, hydrogen is always +1, unless it's bonded with someone really electronegative, or less electronegative. So yeah, +1, -1. This guy here is ionic.
Or, could you please call 100?
So,
Or,
as something that's ionic, it's probably going to be its charges. +2 for magnesium, and -1 for bromine. That seems likely. Okay, this one's a bit more of a challenge, perhaps. What's the typical charge on oxygen? -2, unless it's in peroxide, but this isn't in peroxide, so that's -2. Hydrogen's +1. I gotta use like my common sense now to work backwards and figure out what sulfur is. Because if I look at that table there, sulfur could be like a -2, a +2, a +4, a +6. And to be honest, that might not even be a comprehensive list. So the answer is +6. Okay, so your oxygens are contributing 4 -2s, so that's -8. Your hydrogens are contributing 2 +1s, so that's +2. I need all of this to somehow be 0 when I'm done. My sulfur, I have 1 of them. What is this charge going to need to be to make this all somehow negate out to be 0? It's going to have to be a +6. So then sulfur's a +6 here.
please excuse the interruption. Mrs. Orr, can you return to the library? Mrs. Orr, please return to the library.
Can you look at that in terms of sulfate?
You can do it in terms of the sulfate too. You could say that the SO4 normally has a 2 negative charge. Therefore, if the oxygen gives you like a -8, but you need it to give you a -2 when you're done. Because like here, your oxygens is going to contribute a total of 8 negatives. But then the charge of this ion needs to be -2 when you're done. Then your sulfur would need to be a +6 so that it still has a charge still when you're finished.
But even if you didn't break it down like that, sulfate has -2 and your hydrogen there's 2 of them, so you need to have +1 times 2.
So I mean that helps tell you that the hydrogen should be +1.
Okay, but you need each individual.
But you need each
Oh, okay.
individual atom. Now again, this is not actually an ionic compound. the SO4. Like the H2SO4 is actually it's all molecular technically. So these aren't actual charges on them. Does that make sense? Because they're not actually breaking up into pluses and minuses, but we're kind of treating them as though they are. NH3, we just did this one. It's -3 and +1. Water? +1 and -2, that works. Exception time.
+1.
Yeah, +1 and -1. It's pretty much the only time we'll need to have a -1 for hydrogen. I don't know why this got screwed up. This 3 should be like a small 3.
Okay.
I think I screwed that up. So -2 +3. Let me know if I'm losing you. Oxygen is -2 in almost all circumstances, but this is the exception. This is a -1 and a +1.
We'll look for this one.
Okay, well, what is oxygen's charge? -2. So then to make this work, fluorine's going to have to be a +1.
We just changed the charge.
Okay, now here's the thing. This is not actually ionic though, right? Does that make sense? We're trying to take a molecular compound and pretend it was ionic, but it's not. So, I mean, it doesn't hurt to look at the table and say, oh, look, yeah, it had that charge. But even then, that's still not exactly what we're doing here. We're taking molecular stuff and seeing, well, if it was ionic, how would this work? So, yeah, fluorine doesn't normally have a +1 charge, but it has a +1 oxidation number. Different thing, but similar. Yeah, this seems pretty likely to be a -1 for chlorine. And probably a +4 over here for carbon. That seems the most likely scenario of all of
For
them.
the next one, I mean that after when you're done, it has to be -3.
This one also, for some reason, these ones have been like somehow like the 3 should be down here. Like this should have been HCO3 negative, like that. The subscript thing got screwed up somehow. So when we're done, this whole ion needs to have a -1 when we're finished. So like hydrogen is +1, oxygen is -2. So it almost could look like this. You need to have a +1 coming from hydrogen. And then your oxygen is -2, but there's 3 of them, so -6. You need it to equal a -1 when you're done. So you need a +4 for carbon. Good. So you're kind of working backwards. And then this one also I screwed up on. This should have been ClO3 with a little negative sign. So oxygen is -2. You have 3 of them, so you have -6. But when you're done, you need to actually have a minus left over. Chlorine is +5. Which actually is one of its charges, apparently.
Oh, chlorine.
What was that? That means that, like, in this case here, it's not actually balancing out to be neutral. It actually has to balance out with an extra negative.
If that's positive, we do the opposite.
Yeah. Does that make sense? Okay. Well, we use these then. I just want to go back one last time here to look at, like, say, this example here. If you're stumped about who gets oxidized and reduced, use oxidation numbers. Find everybody's value and then figure out whether the value goes up or down. Because if you go from like a positive to a negative, you've gained electrons. But if you go from a negative to a positive, you've lost electrons. And that'll help you figure out who gets oxidized or reduced. Sometimes we're actually talking about an atom being oxidized or reduced, rather than like the whole actual like compound. What else have I skipped here? Oh, yeah, let's just do this in examples here then. So, let's find some oxidation numbers now in like a written equation. Zinc as a solid by itself, 0. Don't overthink it, sometimes it really is this easy.
Okay.
Hydrogen right here has a +1 charge, so +1. Zinc right here has a +2 charge, so +2. And then hydrogen right here?
0.
Good. Why? I told you it was always +1, but no, this is elemental, like atoms of hydrogen, not ions of hydrogen. So,
Why? Oh, because it's just like.
because this is a neutral like atom, not an ion. It's an elemental form, so it's a 0. If I were to then ask you who got oxidized and reduced, you could say, well, look, hydrogen went from a 1 to a 0, so that must have been gain. an electron. And then if this one went from 0 to 2, it must have lost electrons. So then if this guy lost electrons, he was oxidized, and this one was reduced.
Didn't he gain 2 electrons?
To go from 0 to 2. But if you gain electrons, you become more negative.
Never mind, you go to minus 2.
Good?
Yeah.
Okay, let's do another one. This one's screwed up. There's supposed to not be a 2 right there. Yeah, I screwed up. Alright. So on this one here, let's start with this oxygen. He's a 0. Normally oxygen's a -2, but it's actually oxygen as a element, right? So it's a 0. Here the oxygen is -2 now, and here it's +1. And then over here, this is one of those exception ones. So -1 and +1.
How does oxygen move 2 different?
Ah, I told you this was going to come up back again later. Oxygen goes from -1 to -1 to -2. And it also goes from -1 to 0. We have a name for this. Does anyone remember what happens when the same thing both oxidizes and reduces?
Disproportionation.
That's it. Good. So, circle, highlight, put something next to this one here. I've now maybe gotten far enough to show you a better example of disproportionation. The same thing both lost electrons and gained electrons, and that thing was oxygen. That make sense? So this one right here went from -1 to 0, so that means it lost electrons. And this one went from -1 to -2, which means it must have gained the electron. So therefore it's disproportionation, that's what we call it. The other name for it is auto-oxidation. You might see that as well. Long story short, the same species is both gaining and losing. It's like a bank. It's lending money and it's taking money.
At the same time?
At the same time. You could go in and deposit a check and then immediately take money right back out of your bank account. That makes sense?
The thing with the
Okay, maybe my analogy's not perfect. I thought it was pretty good.
So hydrogen is not anything?
Which one? Oh yeah, hydrogen's a spectator ion then, because it started at +1 and ended at +1. Okay, well, carbon is an element and oxygen is an element.
Carbon by itself is C4.
It doesn't have to be, it could be just carbon by itself. C4 is another possibility though. Or C like 20 and 2. And those are called allotropes. And the carbon has a million of them. If this oxygen is -2, that carbon is +4. So then carbon must be losing electrons to become oxidized, and oxygen must be gaining electrons to become reduced. Okay, I want to make a quick note on this one here. If I were to have asked grade 11 you what kind of equation this is, I would hope that you'd say that this is a formation equation. But it is also a redox equation. It can now be both. It can be a formation redox. Does that make sense? So it doesn't have to be one or the other. It can actually be both. One last one, then I think I'm done.
Wait.
Okay.
Sorry. Does that mean that like the first one is a redox too because it has both of them?
All of these are redox, yeah. Because whenever you have something gaining and losing electrons, it is redox.
Okay.
For the CH4, because carbon, is that hydrogen at -1 or is that +1?
This one right here.
Yeah.
Well, the hydrogen will be +1.
Also carbon, what is
This carbon's -4 then. Oxygen will be 0. This will be a +4 and a -2. And a +1 and a -2.
So is the oxygen doing the disproportion?
Well, okay, so it's not going both ways though. It's not gaining and losing. It goes to the same, like it goes in 2 different locations, but either way oxygen is gaining electrons to become reduced. Who's losing electrons?
Hydrogen.
Nope.
What?
Hydrogen is a spectator.
No, I thought carbon was.
No.
Carbon goes from -4
Plus,
to +4.
so we lose 8 electrons.
Yeah.
Why can't you?
Hydrogen is a spectator.
Yeah.
plus one.
What if
Carbon.
you mixed carbon to be plus, like for the first one,
Okay, but
plus 4 and minus 1?
okay, but carbon is not less electronegative than hydrogen is, though. Does that make sense? You were trying to apply that exception, but that's not going to work here because hydrogen will not be able to beat out carbon for those electrons. So carbon will be the negative one and hydrogen will be the positive. So then carbon is actually the one losing a lot of electrons, so it's oxidized. If I were to ask grade 10 or 11 students what kind of equation this is, hopefully you'd say it's combustion. But now you guys know that it is combustion and redox. Yay. Many things that you've learned in the past. You know how I've told you in the past, sometimes I tell you partial truths? That'd be a good one. When I told you in grade 10 this was combustion, well, I was not lying, but there's actually more to it than that. You could also consider it to be a redox reaction.
Told us it was redox last year.
Probably, like,
Well, my brain
yeah, like that was beyond you at that point. But hopefully it makes sense now. Let me show you an example of something that's not a redox reaction. Let's try this one here. So Aiden already picked up, this is a double replacement reaction. If I try to assign everybody oxidation numbers, it seems pretty likely this will be +1 and -1. I just kept it simple. +1, -1, +1, -1, +1, -1.
No, things change.
If nobody changes their oxidation number, which is similar to their charge, then this is still double replacement. It's just not redox. And I've seen them give questions like this a lot on diplomas where they'll give you 4 reactions and they'll say which one of these is a redox reaction or they'll say which one of these is not a redox reaction. And the best way of solving it is just use oxidation numbers and see which one doesn't have numbers change or which one does have numbers change. As soon as you see a number change from like say a 0 to a 2, you know it's a redox. You don't even have to finish the rest of the question to be honest.
Yes.
So when I started class today, I kind of suggested that I've already taught you these oxidation numbers. Do you guys agree that you kind of had these skills going in? It's just now I want to give you more background on it. They are basically charges. But technically molecular things do not break up into anions and cations. They share electrons. So that's why we're not calling them charges because they're not actually charges. We call them oxidation numbers. But boy, that's pretty much the same thing. Easy peasy? Cool. Hopefully. Okay, that's all I got for the day. So take a break. When you come back, you guys can have some work time. Next week, we're going to do a lesson Monday. I totally spaced on this. I told a few of you we didn't have a quiz next week. We do. We have a quiz on Wednesday. Sorry, I forgot.